Okay, so let's think about mass flow rate, volumetric flow rate. We've got a garden hose attached with a nozzle. It's used to fill a 10-gallon bucket. The inner diameter of the hose is 2 centimeters. It reduces to 0.8 centimeters at the nozzle exit. If it takes 50 seconds to fill the bucket with water, determine the volume and mass flow rates of the water through the hose, the average velocity of the water at the nozzle exit. All right, so as it is going through the hose, we want the volume flow rate, V dot, and we want M dot. All right, volumetric flow rate. We have lots of equations. It's really volume per time. Did you notice this? It takes 50 seconds to fill the bucket. The bucket is 10 gallons. If we want the volumetric flow rate, V dot, the volume over time, they actually gave us the volume over time. It fills a 10-gallon bucket over 50 seconds. I'm going to change that to, instead of gallons per second, we could do a few things. I'm going to do liters per second. So I'm going to change gallons to liters. Yeah, because we're in centimeters. Let's go to liters. We could look on our conversion chart, conversion factor for volume. But 1 gallon would be 3.785 liters. All right, so 10 times 3.785 divided by 50.757 liters per second. That is the volumetric flow rate. All right. The mass flow rate would be rho times the volumetric flow rate. Or, I want the mass per time, and I've got liters per time. Well, if I knew the density, right, then I could, units help me out here. I could change that volumetric flow rate to mass flow rate. So what is the density of water? Well, my first line of thinking, the density of water is 1,000 kilograms per meter cubed. But a meter cubed is 1,000 liters. I'm not sure if we actually have this anywhere on our formula sheet or anywhere. But I don't know if you knew, water, 1 kilogram is 1 liter of water at sea level, standard density. So that's what I'm just going to use. So this one is actually interesting. Taking the density times volumetric flow rate, 0.757 liters per second, 0.757 kilograms per second. Now, volumetric flow rate will not be equal to mass flow rate every time, but I guess it will be if you're looking at liters per second and if you're looking at water, kilograms per second. All right, so anyway, there's the M dot, there's the V dot. All right. Part B, how about the average velocity of the water at the nozzle exit? Well, I could use M dot equals rho VA. I know the M dot, I know the rho, I know the cross-sectional area. It reduces to, well, a diameter of 0.8. I could find the cross-sectional area. Or V dot is V times A. Yeah, either of those would work. Let's do V dot equals V times A. I know my V dot is 0.757 liters per second equals velocity times cross-sectional area of a circle, right? If it has a diameter, it's a hose, it has a diameter of 0.8 centimeters. Okay, 0.8 centimeters. All right, let me think about these units here. This would be pi by 4 diameter squared. Pi by 4 diameter squared. So yes, this would be 0.008 meters. Square that. Square that right there. Okay, but would these units work out? On the left-hand side, I would have liters per second. On the right-hand side, what's my velocity? Maybe I want meters per second times meters squared. I would have meters cubed per second. I would have meters cubed per second on the left-hand side. Liters per second on the right-hand side. Doesn't exactly work out. Maybe I should have had my volumetric flow rate in meters cubed per second. So let me convert liters to meters cubed. 1,000 liters would fill a cubic meter, right? So meters cubed per liters. There we go. Meters cubed per second on the left-hand side, meters cubed per second on the right-hand side. So now I can divide that over, solve for the only unknown in that one equation is velocity. That's velocity, 15.1 meters per second. 15.1 meters per second. That's going to be helpful. We're going to need to find velocity sometimes because of kinetic energy, right? Because we might need to find the velocity at the inlet, might need to find the velocity of the outlet.